Hi, my name is Mariana Robles, and this is my lab report for Lab 3 on black holes and orbits. Here's the table of contents, what we're going to do in this presentation. Firstly, the introduction. The overall purpose of this assignment is to simulate and analyze the motion of celestial bodies to estimate the mass of a black hole and explore gravitational orbits. For part one, we're going to estimate the mass of a black hole. And then for part two, we're going to calculate the gravitational forces acting on the moon and spaceship and determine an initial velocity that allows the spaceship to orbit both the planet and the moon without crashing. For this lab, we first need to consider important equations that help us um, go through the lab. So the momentum principle states that the net force acting on an object is equal to the rate of motion of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here how deriving from the momentum principle, we can obtain the velocity update formula. And this formula allows us to determine the object's velocity at each time step when dealing with a non-constant force. Once we have the updated velocity, we can then use the position update formula to predict the object's future position over time. And then we also have the Newton's law of universal gravitation, which states that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. And then for the net force, we have the perpendicular component, which points towards the center of motion, and in this case acts like the centripetal force. And then we also have the parallel component, which points towards the direction of motion, and which can be changed depending on the object's speed. Now for the application of this lab, the first part, the seed, is everyone's email, so it can assign each student random values. And then here in red, it's not something we edited, but it's the start, it's what the program uses to predict the star's velocity. And here is all the data that we changed, including initial and final velocity, initial and final momentum, change in velocity and momentum, calculating the net force, calculating the parallel and perpendicular component, and lastly, the last box will print out the mass of the black hole, which is the output. Here we also edited so that the arrows can look how they're supposed to. And then we got that the mass of the black hole is 7.71509 10 to the 33. And then for this, the system is the star and the black hole, which is the only interaction we're analyzing, and the surroundings everything else. And for part two, we need to consider gravitational force on the moon by the planet, gravitational force on the moon by the moon, net force on the moon, gravitational force on the spaceship by the planet, gravitational force on the spaceship by the moon, the net force on the spaceship, and then lastly, the output is going to be updating the position for the moon and the ship trajectory, which is everything that is highlighted in red. And then what we got as a result is the initial velocity for no crash is negative 28,500, 24,500 meters per second. And for this, the system is the planet plus the moon plus the spaceship, and their mutual gravitational interactions determine the motion, and the surrounding is everything else. Now for the conclusion, some possible errors that could have occurred were computational errors, neglecting other forces, time stepping up approximations, and then treating the star, planet, and moon as point masses. Now, what does this mean? We have to think about what rate of change of momentum means and what net force means in terms of things you can observe and measure. For rate of change in momentum is measured by tracking how an object's velocity, both speed and direction, change over time. And net force is measured by summing up all the individual forces acting on an object, often inferred by observing the resulting acceleration. Both concepts are tightly linked, as Newton's second law tells us that the net force acting on an object is equal to the rate of change of its momentum. Now, for the second question, to predict the motion of an entire system accurate, your computational model must account for every significant interaction between the constituent parts. This means including the fundamental forces, such as gravitational force, the contact and frictional forces, for systems where components interact through collisions and direct contact, modeling elastic and inelastic collisions, friction, and deformation is essential. Then external influences such as environmental forces, air resistance, or boundary conditions that should be included. Now, regarding dominance, it often depends on the scale and specifics of your system. For dominant interactions, in many cases, one type of interaction overwhelmingly dictates the behavior of the system. For instance, in this scenario, the interaction between the black hole and the star will be more dominant than the interaction between the planet and the star because of their masses. Shout out to Cesar. Thank you.